I'm Thao from Applied Artificial Intelligence Institute at Deakin University, Australia. And today I'm gonna give you some talk pretty much from my research that presented elsewhere. So yeah, some short introduction about myself. I'm currently a senior PhD candidate at Deakin University, as you know. And I graduated from Tokyo Institute of Technology in Japan and Hanoi University of Science and Technology 6 years back. And I'm having interest in applications of machine learning and computer vision in general. More specifically, I studying how machines talk and what they see and how to reason from what they see. For the talk today, I would like to cover some contents about the introduction to visual question answering and its application in real world. There are a whole bunch of literature in visual question answering thus far. But in this talk, I will mention only some very general approaches. Instead, I will spend more time to talk about my two recent papers. One is about dynamic language binding in relational visual reasoning. That will be presenting in Izikai in 2021. And the other one that I presented in CVPR this year, Hierarchical Conditional Relation Networks for video question answering. So I will explain the difficulty to go from like still image question answering to dynamic video question answering. And at the end of the talk, I will give some summary of the talk, some highlights of the talk today, and discuss some future directions with you all. If you have any question to ask, feel free to interrupt me on the way. So the task of visual question answering is that you given an image or a video and a free form natural language question about the visual contents, and you try to build a AI system that can answer the question accurately. For example, for those who used to works on visual question answering or has some background on this, already knows this very famous example of very early days of visual question answering. So the question is, what is the mustache made of? So we would expect the AI system to give the answers bananas. Yeah, so that pretty much what it is. So there's a demo online of visual question answering available that you can try it yourself. I'm gonna show you one or two examples. So for this demo, you can choose either one of the two VK models that very well known in the field. One is Partia, another one is Hierarchical co-attention back in 2016. And the Partia is, yeah, it's much better than the other one. I will pick a random image here to show you how it looks like. You also can upload an image yourself and try to type in some question and see how it's answered. So I just type here an answer, a question. Is the mother sitting on the left? So the expected answer will be no, and the model just get the answer correctly. You also can type a different different question like how many people in the photo, in the picture. Then the answer would be 2, yes, with like high confidence. So that how it look like. You can try it later. I will post all the material online later, so you can you can have access to the link there. Okay, so let me try to motivate a little bit why the bridging research of vision and language is interesting. So first, the first motivation is that nowadays visual content is like all around us. You can have very easy access to the picture and image online. There's a report that there are more 3 million images and videos uploaded on online on like social media platforms such as Facebook, on Twitter, and Instagram nowadays. And the second point is language is how human we communicate. So if we have a way to connect vision and language, it will enable many applications that we can come up with. I will go back to the application of visual question answering or very soon in a couple of slides. So many problems can be formed as visual question as question answering problem. Let's say we have like recognition task. We can ask a question, what is present in the photo? That pretty much the recognition task that we do all back in the history of the computer vision field. And the equivalent question in the video will be what action or event is in the video. So that is an example. I show how to like convert a computer vision task into a form of question answering. So solving question answering is pretty much equivalent to solving few sort multi-task learning. It requires machine to solve many problem at once. So then why I said it feels short multi-task learning here, because the number of questions given a specific image or video is like almost infinite, due to the fact that we can have multiple ways to present a question of the same meaning. Let's say you can ask, what is the red things in the photo? Or you can ask, what color is the fire hydrant in the photo? Yeah, they're pretty much the same meaning, but like we have different way to express that. So we can have like multiple ways, even in different languages, we can have like infinite number of questions of the same content, right? So from the AI perspective, VQA is the intersection between many subfields. Let's say computer vision, we have natural language processing, we have machine learning and reasoning. Let me explain a little bit about the example here. We have a picture like this, and we got a question, what can the red object on the ground be used for? So first we need NLP first to understand the meaning of the question, right? And then we need object detection in computer vision to detect the red object in the photo, which we don't even know what is the object used for. We only know that location, in that location of the image, we have an object, which is the red object that the question mentioned. And then we need machine learning and reasoning to connect the knowledge we have in the support fact to arrive the correct answer. However, a support fact is not available in most of the time. So it's really a model needs to reason from like available data, or it's have to acquire this kind of knowledge somewhere else. For example, via transfer learning or knowledge retrieval from published sources. For example, we have Wikipedia, like published sources that we can have access to. You can imagine the difficulty of this kind of task, even if you ask a baby, a child, if she or he would answer this question, given he never see a file hydrant before. This was very difficult. So this diagram presents the information hierarchy for images and the knowledge associated with each level of information required to solve visual question answering. So it's a low level image processing. It's required the understanding of object features, such as we have like color of the object, we have shape of the object, and other object recognition, including the recognition of invisible objects such as action or events. So we need to understand the relation between objects. We need to connect different action and event together to able to recognize what kind of action or event present in a video. Other scene understanding, we need to understand the complex relation between objects and event and activity over space and times. Even common sense knowledge might be needed. For example, given a picture of a pizza, and a good model should be able to tell whether a pizza is vegetarian pizza or not, based on the existence of meat on the pizza, right? So that's the sort of thing we refer as common sense knowledge that like the model itself would not understand, but like somehow we need to give it the knowledge, the background knowledge to be able to answer that. As you can see, each level of information, such as low-level image processing, object recognition, or scene understanding by itself, is a very difficult research problem, and handling them all together is much challenging. Let's talk a little bit about some application of visual question answering in practice. One application of visual question answering is to assist visually impaired users who have access to natural language but can't see things. A visual question answering system in conjunction with like speech to text system would help them to have access to visual content by asking questions and getting response in natural language form. Another application of VQA is in security surveillance, where you have to deal with like a huge amount of recorded data. So VQA system would allow people to retrieve information much faster. Let's say you have a recorded video of many hours, and then you want to trace back like a piece of information where a man in red shirt enters a building. Then you ask like a relevant question, and the output will be like the piece of information that you are querying. In this sense, Google video search is an example of the use of video question answering. But like note that the performance of video question answering, even in like Google should, I mean the Google video search is not great at this point. We have like a lot of things need to be done. Compared to like still image question answering, video question answering is like much lags behind, because the expensiveness of computation and like the too many factors that we need to use at once. So like people pretty much focus on how to solve image QA at this point, while like much less attention to focus on video question answering. So there are three types of question in visual question answering. The first one is open-ended. So we have a question like, is this a vegetarian pizza? And the model, I mean AI model, have to output an arbitrary answers, which is no in this case. We have another type of question, which is multi-choice question, pretty much like human. We do tests. So model have to choose one or multiple correct answers from a list of answer choices. For each type of multiple choice question, we will have slightly different way to encode the output during the answer decoding. And the last one is counting. So we ask model to count over time or like over space, over spatial space, which is in the image. For example, we have a question, how many slices of pizza are there? We would expect the model to give an answer, which is 6 in this case. All right. I would like to give some example from like VQA dataset, so you would have a sense of like what sort of problem people are dealing in like this vast field, because you know, as the question is arbitrary, we have many different ways to I mean, we have different angle to ask a question, and it's mostly impossible for a single model to answer all of those things. So let's say in this case, we in the VQA community, we focus on different aspects of like visual content. So the first one is perception, which pretty much like recognition that we doing during the entire history of computer vision. So the question would be like, what is this in the picture? Or we can ask, the second question, is this a vegetarian pizza? Or a little bit about reasoning, but it's not really shown. The second type of task we're dealing with here is a relational reasoning. So we obtain new knowledge based on the relationship between objects and entity presented in an image or video. While the last one, much more complicated, we have multi-step reasoning. So to be able to arrive at the correct answer, we will have to go through multiple steps. Let's say we have the question, how many objects are there? Either small cylinders or metal things. So we first have to locate which one is small cylinder, which one is metal things, and then we will go back to how many objects are there, right? For the second one, we would have to go through the large things in the photo and the metal spheres, and then we have to compare them together. So we have to go through multiple steps to be able to answer these questions. This is from like human perspective when we answer a question. So different model will have a different approach to solve these things. Some universal models, they try to combine all of those, and hopefully we will have a like universal model which similar to GPT that you might heard about the NLP field recently. But we are very far from have that capability in like visual reasoning field.
Thao, question about the data sets. Maybe you will be talking later, but out of curiosity, first of all, how large are these data sets, or how many photos are there, and what is the size? And also, how much text is there per photo, or how much like reasoning information, and how do you quantify reasoning information per photo exists?
Yeah, it's really depends on the data set you have. So those are pretty those three here, the pretty big data sets. So for the first one, we have like pretty much 1 million questions. Mm-hmm. I'm not exactly sure how many photos we have, but pretty large. And like a large portion of question in the first data set, because it's proposed back then in 2015. So like they almost focus on perception. So if we have a very powerful object recognition, and we have very powerful classification, then we would have very great performance to answer this data set around. I think now the state is just like 7 72% accuracy on this particular dataset. Why in this case, in the GQA dataset, the problem is much more challenging. Because most of the question is about the relation between objects. It's not like single object itself, but even if you accurately detect an object in the photo, it's not guaranteed that you can give the correct answer at the end, because you have to look at the relation between that object and the other object. So this one, we have like more than million question answering pairs in the training only, and you have another couple of millions question answering, question only in the test sets. So you will, if you train, after you train a model on the training set, which is like more than 1 million question, and you upload it into a cloud server that run by the original author of the dataset, and you have the performance of the models that you train on the the training sets on their test sets. So basically, you don't have the graph tree for the test sets. Only the author have. And for this one, you have 70,000 images and 700,000 questions. Wow. For this data set. And this one is a synthetic one. So actually you can have like infinite number of images and question as you want, because they provide you all the program to generate question and all the program to generate the images. The only difficulty here is like you have to increase the number of the objects. I mean, you have to have different more variants of objects out there, because the number of objects in this particular dataset that publicly available online is not many. So if you increase the number of images and quite a number of questions, then you're likely to input some like bias information into the dataset. And in terms of statistical perspective, it is not good, because like your model the model you design will have a tendency to learn the pattern behind the way you generate the data, which is no good. And we don't want to do that. We want to avoid from that one.
But still very, very elegant way, because the next question was, how do you annotate a million questions and answers? So they solved this, but the other two, it was interesting to understand how they did it.
Yeah. So it's a very long process to gather this large data set. And it's like huge effort of the community to be able to build this kind of data sets. Yeah, and most of them are very top one in the field that would be able to, like they have resources and things to annotate this kind of data. But like I believe that VQA and other field in computer vision will move to like unsupervised learning more in a couple of next years, so we can get rid of the problem of annotation like this. Human annotation is like has its own limitation.
So now I have a question, but after a few slides. So how do you think unsupervised learning here will work? But I think maybe we could address it after you show us.
Yeah, I will back to that kind of question at the very end of the talk, because I also mentioned some like direction in the future. That what I actually keen to work on too.
Okay, cool.
So yeah, so probably I have to go a little bit farther, otherwise I will run out of time. So here some data set for video QA. The one in the left is like real world videos. While in the right they are like synthetic one that resembles the one that I showed in the image question answering before. I would like to talk about a little bit about the most recent one, the cleverer one. which introduce 4 complex reasoning tasks. One is spatial temporal reasoning. The second one is causality, a relation between events. The next one is predictive reasoning, which like you ask model to predict what happened next after the movie, after the video ends. And the last one, you ask a model, what if a particular event did not happen? What gonna happen if that case happened? So that very, very challenging problem, and it's come from a very new perspective. That I think like future model will focus more energy to solve this kind of problem. And the more complex form of video QA is movie QA, where it's not only visual content matters, but also the conversational contents between characters matter. Like if you watch a movie, you not only focus on the visual content of the movie, right? You focus on the contents, how people interact with each other, what is their, like the utterance spoken by the characters. You would like draw attention more on that. And this is like the whole new story that you need to handle. And it's much more difficult from what I show here, which is only like people perform some particular action and you ask about that action is much less difficult. Okay, so here's a common approach of VQA. VQA was first introduced in 2015 when deep learning is blown up. So you would expect to see most of the models, if not all of them, as based on neural networks. In general, a VQA model includes a visual feature extraction, a language embedding, and then you merge them together before fitting into a answer predictor for final prediction. Mathematically, VQA is to deduce an answer I title here from a set of predefined answer set by a model P taking as input an limit I and a question Q. And there are large body of methods as I mentioned much earlier for VQI, but I only picked a very simple one to explain here so you have a sense of how people approach to solve the problem. So the first VQI model is introduced by Agrawal in 2015 when he first introduced the task and the VQI dataset. The visual part is extracted by a VGC net trained on ImageNet for visual extraction. The output is a vector of 4096 dimension. And the question is first embedded by backup words, and then backup word is a method to embed like natural language words into vector space, and the distance between two vectors will represent the similarity in terms of semantic between two words, and then they fit into a LSTM to like to model the sequence of the question, and the output of the very last step of LSTM will be used as a representation of the entire question. And then they concatenate the two vectors together, fit into a classifier of 3 fully connected layers before going through a softmax function for probabilities of each answer. And the one with highest probability will be chosen as the correct answer. Yeah. Before I move to the next paper, does anybody have a question?
I think Stanford here, he had a remark. The question originally was, is it both NLP and CV here? Yeah. So of course, but then again, the following question is NLP, CV, and then NLP again. The output is a natural language processing based.
Yeah.
Mm-hmm.
Yeah. In terms of my work, I don't like really work on NLP because it's like common practice of NLP field. Yeah, at this point, I don't work much on NLP, but of course, like basic question about NLP, I can take question as well. Okay, in this section, I will talk about our Izikai paper on image question answering, which more focus on relational reasoning. So in earlier slides, I have mentioned that reasoning plays a crucial role in visual question answering. My research set this aspect as the main focus. To have a better clarification why reasoning is important, I will explain the difference between like VQA model where reasoning capability matters and VQA model where reasoning capability doesn't matter. So here, let's say the object recognition task that we often see in computer vision, we can form it as a VQA task, which is what exists in the photo, right? So a very simple neural network, which with a couple of layers can give you a trustful answer for this kind of question with like high confidence if the network is trained on a clean data set. So there's no reasoning needed for this kind of task. You just look at what kind of things presented in the image, and then you can give an answer, which is a cat. Considering more complicated scene where the one in the right hand side here in the slide, we can have a question equivalent to the object detection task like this is where do the objects locate in the image, and like some modern neural networks, models such as fast HCRN or Jolo can handle this quite okay at the moment. And so how about this kind of question? We have a image like this, and we have a question like what color is the thing with the same size as a cyan cylinder. So the same network that I presented before give an answer which is cyan, which is not correct. So why things did not go well? The actual problem here is the system failed because this style of question is very tricky, and the network gets the most common color in the image, which is cyan here. You see there are three cyan, which is the prominent color in the photo, and also the word cyan also appear in the question itself. So it's sort of like the effect by the linguistic bias presented in the question. So and when we train the network, it will be like influenced by that. But the actual reason behind the failure of the network is this kind of question require multi-step reasoning that I explained before. So for this particular question, we will first find the cyan cylinder, and then we locate another object of the same size, and then we determine its color. So we have to answer this kind of question correctly, a model needs to reflect this kind of things in its behavior. Otherwise, it will fail like in this case. So what I just what I talk about is called reasoning. So in general, reasoning is to deduce new knowledge from previous acquired knowledge in response to a query. The query here is mean like the question we ask here. And based on the general definition of the reasoning in the previous slide, I just passed. So the definition of reasoning in the context of visual question answering would be the ability of a model, to train to change the relational predicates to arrive at the final conclusion. To arrive at the correct answer. So with this kind of question, it's essential that a model need to understand the spatial relation of us in a certain context given by the question. I will explain more on this point at later slides. And the second point is training is query dependent. What I mean by query dependent here is that as a human, how we find the correct answer is pretty much depend on how we interpret the question. So even the same correct answer, but like two people might have two different ways to interpret the question, and they will find like another way to arrive at the same correct answer. So how we understand the question at intermediate time step would be very important. How we train the predicate to go to arrive at the answer. And for some predicate and relation, they are important for like a particular question, but like for another question, they are not important. So we don't take all relational predicates available in an image or a video into account at once. We will use like different set of relational predicate at once. Depends on how we understand the question at this point, at that point. And another point is the representation of visual objects should be conditioned on the question words. As there are more variants of an object class, for example, we have cats, but cats have different cats varies in size and hair color and whatever. Language binding would stand out the visual representation of a particular object of interest out of like a whole bunch of other objects. So and we wish to have a model, a system that end-to-end differentiable. So like we can get rid of the painful of training non-differentiable network. For the feature representation, I would present the advantages of going from grid feature representation to reason feature or object-centric feature. So the grid representation is what we see in common convolution networks such as ResNet or like VisiNet. While the region proposal are output of object detection, and one box here on the right present a possible object. So in terms of semantic meaning, proposal and words have the same semantic abstract. Why it doesn't hold in case of grid representation. Let's say we have a man. So a man in this case would be like the whole reason of the man presented in the photo instead of like a grid representation on the left. As a result, we would expect the reason feature are better in terms of interpretability for human being, because like it's the same, it has the same semantic abstract air what a human we understand about the world and objects. And here's what the network architecture that I got out of that assumption and motivation. So we call the model language binding object graph network, or LOGNet. We use faster HCRN for object detection, whose output are bounding box, as you see here. And for the language part, we first embed it with like a common word embedding, and then fit into a bi-LSTM for modeling the sequential information. Different from the previous work, we not only use the final state of the very last step of LSTM as a representation of the question. We also maintain a list of hidden state of the LSTM and refer it as contextual words or linguistic object in this case. So if you understand a little bit about NLP, you would expect the contextual word here would be very similar to the notion of contextual embedding in BERT or GPT that you heard in NLP field. And the LOGNet is a series of log units chaining together. I will talk about the log unit later. So the LOGNet operates on object level for both visual cue and linguistic cues instead of like pixel level that people easily working on in the literature of visual question answering.
Now, can we look back at the diagram just to make sure that it's clear? So the contextual words, those encodings or embeddings, they are passed one at a step to the log units, which are by themselves type of, let's say, more advanced, more complicated LSTM units, right?
So this one is pretty much still like the vanilla LSTM, the bi-LSTM that that people use in NLP. And the question here, that is like the entire representation of the question, and the object words will be fed into every single log init and will be utilized by the log init.
Yeah, so every different contextual world is fed into each different log unit here, or each different instance of log unit.
Oh yes,
build out the flow. Okay.
So
and there are skip connections there, I see, also from the queue, which is the output of the.
Yeah, exactly. So each log unit here will use only a part of the contextual word, the object. Sorry, the linguistic object here. Let's say the first unit will use. We have the question: how many tiny yellow matte things are to the right of the purple thing in the front of the small cyan shiny, very complicated question. So we have different referees here in this one. So each log unit will use different like subset of the question. Let's say the first unit will use the tiny yellow matte things. The second one will jump into the purple things, and the last one will jump into the cyan shiny cube. So we don't use all linguistic objects at once, but we use only subset of it in each log unit, and we chain the subset of linguistic together and reflect that chaining into the visual part, how we connect the visual object together based on the way that we jump from this subset of linguistic to another subset of linguistic. That pretty much is what it.
And that subset is defined by the contextual words in the NLP LSTM below here.
That subset will be learned over time using an attention mechanism. Yeah.
Okay.
So that's what I just explained. Yeah, exactly what I just explained. So it's log units. We have three submodules. The first one is visual graphs constructor. The output will be, you will see like a visual graph here, which connect the visual objects that we detected from faster HCRN. And the language binding constructor will decide how much a particular word influence the affect the representation of the visual object here. And the influence from the linguistic object to the visual object will be represented as a bipartite graph here, as you see on the right side. And after that, we will update the representation of the visual cues beyond the binding from the linguistic object. And later on, for the representation refinement, we will update the representation of visual object based on the information of like visual object in its neighborhood. So this is how it look like, and how we construct the visual graph. So as I explained before, so each object here will be a node in the visual graph. We're finding a way to connect all of objects presented in the photo as a graph, and the edge between any two objects will reflect the similarity and in terms of semantic and like spatial relation between them. That's why mathematically we compute the adjacent matrix of that graph as an outer product between the representation of objects. And you see here on the right, this will reflect like the linguistic object being used in each log unit. You see, let's say in the first step of log unit, because the attention is spread all over all the words, so you don't see any word just shape that like particularly attended to. But later of the network, when you change and it getting converted, you see very clearly only a subset of object, which is like the large mental sphere here, is attended, and the other one is the math block is attended. And that also reflected well in the visual part. You see the graph will gradually convert into like a particular form due to the converse of the linguistic part. All right, is it clear for you to understand?
There are 3 questions here. Maybe we answered them, but still I will ask. Nasib asks, how do you generate a scene graph from a video?
In this case, I'm dealing with an image, not a video in this case. So this is like a scene graph on image, not scene graph for video in this case. But
yes,
I would answer if you want to build a scene graph on video, it will be like the connection between events and activity. You can refer to Li Fei group. They have built a large dataset for scene graph generation on video with the action genome. Very good reference.
So I will add this to ask you later for the references, Li Fei group for action scenes. Okay. And there were a couple of more questions. Yeah, and then also he asks, if you only use image, won't you be missing temporal information?
Yeah, in this case, because I don't dealing with video, so yeah. This our interests in my case anyway.
And another question he had was, can you explain how visual graph constructor works? So I think, well, we explained, I think, in the previous slide. Nasib, let us know if you still need clarification.
Yeah.
In the meantime, also Ina asked, how many log units are required?
Oh, yeah. So it depends on the complexity of the question being asked. So in this case, the question is very long and complex. So I empirically see that it converges very well when we use around 12 log units. Otherwise, around 8 log units is sufficient for other questions. for other data set, which is like GQA data set, for example. Okay, any more questions?
I don't see in the chat. If anybody, a good time to mention again, if you guys have question, you can ask with audio. So that,
Yep.
because Nasib's question was 10 minutes ago and I was looking at the lecture, I didn't see. So feel free to ask when I'm not seeing it.
Yeah, I already explained the language dividing constructor. So I just add some more point here, like why the visual representation depends on the context. So let's see, I have an example here. What is the man holding a glass of wine wearing? So in the scene of multiple men visible. So you would expect which man you are referring to. So the particular man that holding a glass would be referred to. That's why like the linguistic part will help clarify and refer to like the accurate one in the photo, instead of like you have like an unique representation of like human. So that's what I mean by the influence of visual language representation on visual representation. And then at the end of the bipartite graph, I would update the node representation of visual nodes in consideration of word binding, simply by a concatenation operation of visual representation itself and the weighted sum of linguistic words, weighted average of linguistic words representation. For the node representation refinement, I use graph convolutional network to refine representation of visual objects based on the representation of its neighbors. And I also propose to use skip connect graph convolution network, which allows stacking more layers due to its robustness to a gradient vanishing problem, similar to what we see in ResNet. And here are some example of our graphs after the binding. You see, so the binding will tell you what aspect of the visual content you need to focus on, you need to look at. Let's say we have two different sample here. The first one, it's actually a model to look at the color of objects instead of the second one, look at the shape of the objects. So this is the advantage of language binding into the model. And it will drive the model how to change the predicates, relational predicate to arrive at the answer. And some empirical results. We are state of the art on a couple of datasets, including CLAIRE dataset and CLAIRE human dataset. Why we're not able to beat the state of the art on the GQA dataset, which is the last one that I was mentioning before. But like, it turns out that our model works very well on smaller amount of training data. In this case, you see we slightly better than the state of the art, and in this case we like clearly better than state of the art. So we suspect the improvement is from the object proposal representation and the robustness of the model or modeling relation between objects. As in this kind of data set, especially the synthetic one, the relation between objects are like very small. I mean, the number of relations are very small, left and right, like in front and up and back in the back. So only a small number of data are needed to encode the relation between objects. So our model could take advantage of that. So it performed better than previous work. All right, and now I would like to talk a little bit about another joint work of myself with my team on relational reasoning on video QA, which is the paper that we published at CVPR in 2020. So here I want to talk about the difficulties when moving from image question answering to video question answering. So in the video question answering, a model have to understand has to understand the temporal reasoning in addition to visual reasoning, and besides, as you know, the video on even movie is much richer than still images, with possible addition channels such as subtitle and speech, as I explained before. And because of the rich information encapsulated in the video, we can have much wider range of questions being asked in video. Let's say, given a particular video, you can have a lot more questions than given a single frame of a video equivalent to an image, right? So that's why it makes the video QA much challenging than the image QA that I was working on the previous work that I just presented it to you. And in this work, we aim to have a reasoning engine that first, it's effectively reflects the key feature of videos, including long-short temporal relation, hierarchy, compositionality of video. What I mean by like the hierarchy and compositionality of video here is that as a video, we have like video frames, which is like a single image. We have video clip, which is like a set of video frames, and we have video level, which is a set of like short video clips together. That makes the video structure hierarchical and compositional. And the units that we're designing have to be readily extended to handle additional information channels, such as like subtitles or speech information from in the movie question answering. And it can help to ease the model building process by simple rearrangement and block stacking with a generic unit that we see in most of the breakthrough neural architectures, such as ResNet and recurrent neural network. And in particular, we propose a general purpose reusable unit called Conditional Relation Network, or CRN. The CRN is a relational transformer which encapsulate and transform an array of n inputs into another array of like n from items. At the core of the CRN, we compute the relation between like different subset of input items. Let's say we have this network to model the relationship between any two objects, while the other network to model the relation between any three objects in the subset. And then we have another we have another network to inject the conditioning feature, which is the global feature of the entire input array into the network, and output the relational feature at different scales. And the subset in this case are picked on a random basis. And thanks to the flexibility of the CN units that I just explained, and its encapsulating design, we're able to stack them together, like in this figure, in a very straightforward manner. In particular, we propose a way to use CAN to encapsulate the relational knowledge from video objects with activity flows represented by the motion information. At the clip level, the CN will encode the relation between frame appearance, integrates the clip motion and linguistic feature and context. And at the video frame, at the video level, they capture the relation between clip encoding and integrate with video motion and question respectively as contextual feature. And it's also capable to go deeper into the hierarchy to deal with like long video. You can stack one more layer between the clip and video model, video level to handle longer video. So it really depends on the depth of the hierarchy you want to deal with.
I have many questions, but I think Dan, you had a remark. Go ahead.
Yep. Yeah. So here are some empirical results. We are stated that.
I think we have a question from Dan, and then we have at least two from my end about the CRN structure. Go ahead, Dan.
Okay, so probably I will skip the empirical result because you could imagine or you can just go directly to my CVPR paper to have a look. So basically, we got a very good.
Is it Thao? Is it okay if we ask a couple of questions?
Yeah, sure. Okay. Sure.
So Dan one on the audience, he has a question for us.
Yep. The CAN unit or the CAN network?
I need the previous slide, but he had a remark, maybe I'll say, and then we can start the talk from there. So he mentioned on the comments in the text, video usually also allows a much better 3D reconstruction than from one image.
Yeah, that's correct.
Yeah. Dan, feel free to join in. I think you wanted to say something. And
where's he sending question from?
He's in the text, but he also now with the audio tried, maybe he's having problems with the audio. In the meantime, I think I will ask the questions that I had also.
Yeah, sure.
So basically an encoding, it's going to be an encoding of a clip or an encoding of a previous CRN layer.
Yeah, so you can see here the CAN at the video level will take as input the CAN at the clip level.
Mm-hmm.
So the output of the CAN here go into the CAN at the next level.
But if you look at the CRN here on the bottom part, it gets does it get images? Does it get just pixel information, or how does it?
Oh, okay. Here is a frame-wise feature here as a like the feature extracted from CNN model, which is ResNet feature in my case.
Okay, and if you can go back again to the previous slide. Conditioning feature C. So I think this is the one that gets the question or gets the clipping encoding or the video encoding. Is that correct?
So the conditioning feature in this case, it can be anything that represents the global information of the input set.
Mm-hmm.
So let's say if you have information that related to all items in the input set, then it can be a very good candidate for the conditioning feature. Let's say that's why I pick like question and motion as a conditioning feature, because the motion like well related to all, it's extracted by the relation between all frames in a clip, right? And the question here, a single question will relate to all frames in the clip.
Oh, okay, I see. I understand.
Yeah, that's why it's
a lot of work you guys did.
Yeah, so you imagine that this one can like give complementary information for the input set, or it can be like a filtering for the input set. Let's say you have a question here, and the video contents will be very redundant to the question, in the sense that you only interested in a particular part of the video, not the entire video. So the question here will act as a filter. It will filter out all the information that not related to the question by a multiplicative operator. So all the information go after condition or after conditioning on the question will be relevant to the question only. So that's the flexibility of the CN unit. And it's actually the beauty of the unit.
And those G's and H here, what exactly are they? Are these LSTM units or?
Oh, they are just feed-forward network in this case.
I just feed forward?
Yeah, but yeah, but you can use LSTM because it's like temporal, right? It's a sequence, so you actually can use LSTM.
So it's in the feed forward case, is there a set amount of neurons there, or?
Yeah, just a set amount of neurons. I just concatenate the feature together and then fit into a feed-forward network.
That's so, where you had the 2, 3 tuple. You decide in advance how many tuples you use, and based on this, you choose the amount of neurons.
Yeah, exactly. So if you see it as a like a step of LSTM, then that's it.
Yeah.
So I just introduced the concept. I mean, this concept of CRN, it will have that properties. So any subnetwork can be used H and G here if it satisfies like the property of the input feature. Later I will talk about when I expand the work into movie QI. So it's not stop at visual content only. It also can handle like documentary. It can handle textual feature, which is this one. So the movie QI is like this. You have the movie content, right? Then you have subtitles, which is like a bunch of text, a bunch of utterance from like speaker and characters. And then you have to do question answering. So this is how the HCRN look like when it's deal with this kind of thing. So the visual stream is like pretty much similar to what I just presented, but the subtitle part, like the CRN now will take as input the utterance of speaker, the utterance of character instead of like visual feature, and it proves that. And I got like pretty okay empirical result, proof that like the CRN is generic enough to work on like multiple type of input data. Yeah, that's the entire point that I want to make out of this work. And it's a very, very long work to do actually. I cannot explain very detail of all the single unit here I have in a couple of minutes, but yeah, that's the general idea I have here.
It's a good time to ask, how long was this research, the theoretical part and then the empirical implementation part?
Oh, it took me quite a bit. I think it's taken me 7 or 8 months to dedicatedly work on this project.
You by yourself 7 to 8 months thinking of the structure?
No, this is a joint work with my advisor team, and at the very beginning, I work with 3 other people. I don't work with them, yeah.
Okay. And
all right.
Go ahead.
Yeah. So yeah, I just want to mention some future direction. The problem with the current VQA, including image QA and video QA, is the generalization and the consistency of the VQA. Let's say there's a image and you ask a model, "It's raining?" It say, "No." Um, uh, but like if you ask us some tricky question, like are people wear raining coat, then it probably will answer yes. So it means that the model doesn't really understand the semantic of the question itself. And it's pretty much like the model overfit into the statistical pattern inside the data it trained on. And that is one of the great directions that people digging in. Another one is the transformer-based method to solve vision and language tasks, especially video and language tasks that you were talking earlier on unsupervised learning methods on vision and language. Is like getting more crowded lately? And another direction that I feel very promising is the object-centric for video QA and video understanding. So, but you have to deal with like object tracking relation across space-time and causality between activities and events. That would be much more difficult, and your model have to like present and represent the interaction more explicitly. In the current effort, those things pretty much implicit in the feature. That's no good for interpretability, but object-centric will solve that, and people are working on that too. Yeah, that's it. So today I introduce you all to the basic of VQA, its application, and like my work on image QA and video QA. And yeah, so you would understand the general idea of the field itself. Thank you so much for having me today.
Thank you, Thao. Thank you. It's a good time for questions if anyone asks, if anyone has. I always have, so I will be the last to ask. I see Uri is asking here, did they try to understand intermediate representations of the network stages to see for semantic deviations? Is it making sense?
Yeah, so in the video work, I mean, in the HCRN work, we wouldn't be able to do that because like the relation here is like too complicated, and we couldn't visualize it very well. We could only tell it from empirical results. But if you back to the work on image, is much more transparent. You see what is actually the model look at. You see what actually the model from the data.
Any more questions?
Hi, Thao.
Okay.
Oh, sorry. Hi, Thao. Can I just ask? Thank you for the presentation. I kind of understand the flow of how you're doing things. Can I just ask with regards to like movie VQ and VQA, right?
Yeah.
Would it actually be more? I mean, have you all considered actually taking in the audio of like a particular video sequence and putting that as like part of the contextual data for inferencing? Because it seems to me that a lot of videos usually requires I mean, when we look at a video, we usually use the audio to try to understand what the video is about as well.
Yeah, yeah. Your concern is valid. I mean, like a lot of people also have the same question, the same concern. The only problem with the speech processing is it's very noisy. So I'm not sure because I'm not working directly on the speech recognition system. So I'm not sure how accurate the system are now. But you can see the subtitle here is pretty much the same with the audio. I mean, in terms of contents, I don't mean the data, but I mean in terms of content, they are pretty much the same. So I think if HCRN in my case could be able to handle the subtitle, then probably it will be okay to handle the speech information too. But the problem, how to represent the chunk of the speech, the chunk of the speech information would be a problem. And I'm not familiar with the literature on speech processing. So yeah, sorry, I can't have a very great answer on that one.
Oh, it's okay. It's okay. Thank you.
Thank you.
Can I ask a question?
Yeah, sure, go ahead.
So I am not, VQA is not my area, and my question is like high level. So, and the first one is the system is limited to questions that can be asked? And the second one is is always there is an answer, and let's say, how do you know that there is a failure in the system in real application?
Oh, I'm not sure if you are here from beginning of the talk.
I think that yes, but
yeah.
I don't understand. So how? When you ask a human a question, he can tell you, I don't understand the question. I don't know what you are telling about. So here, here is everything is like, there are words, there are visual words that are like these boxes that are found, and there is a relation between them and so on. And but is there some constraint on the questions that can be asked? Can I, for example, in this sentence, what does the boy with a brown hoodie do before running away? For example, I don't know the word hoodie in English, but but I look at brown and I understand that it is man, and so hoodie doesn't matter for me. So there is a lot of other things that as humans we do, and also let's say do before, let's say the running away is very meaningful in this sentence. So if there will be some word that I don't know, I can't answer the question. So, and this is what I don't really understand from, let's say, above level. So what are the constraints on the system? So what are the constraints on the questions that can be asked? What are like other cases when the system tells, I don't know how to answer? So something like this one, and when there is a failure in the system itself, so something like this one.
Yeah, thanks for the very great question. I think your concern is a valid concern. In terms of my work, I would assume that all questions are valid. I mean, the question will be relevant to the visual contents, but like if you deploy this kind of system in real world application, then your concern is should be valid in the sense that many questions there are no good answer from a model, right? So in this case, we don't particularly deal with that, but it's possible to do with that. Like if you train additionally, if you have like additional annotation, whether a question is valid or invalid, then you would change both positive sample and negative sample at once. Then the model would be classified whether a question is valid or not. That is not a hard task. It is just a binary task, because based on the question you have in the training data set, you would know what question is valid and what question is invalid, right? Then you just label them, train them on the model. Then the model would understand if the question you input is is valid or not, is relevant to the content or not. Another way to tell that the question is valid or not is that if the question, if the model doesn't have a very good answer, the probability for the answer will be very uniform. Let's say you have all answer candidate. Let's say you give 5 answer choices, and all answer choices get like the probability of 20%. Then you see the model confuse itself. It doesn't have a very good answer for that. So you say, oh, probably the question and the video contents mismatch. Did I answer the question?
But let's say in the question 1, I just tell, what does the boy with a brown, and instead of hoodie, I tell any other word that does not exist at all. So will system be able to deal with this?
It really depends on the data. If the data support that, then yes, the model will be able to do that. Like, so let's say I have this model, I have this example, right? So now I ask the question: is the mother sitting on the right? There's no mother, there's no woman in the photo, right? You would expect the answer will no. But like the model failed, right? In this case, it wouldn't understand. It will give an answer a yes with like very high confidence. So it means that the model failed to handle the case because it's never seen this kind of question before in the training data. So you would have to do some additional work in able to cope with those things. There are many details that you have to work on to have like the universal model.
But if I understand correctly, instead of word mother, there may be some word that is unknown to the system at all. So I can, it may be even unknown word. It shouldn't be in vocabulary. Or it's always should be in vocabulary. This is my question, because in natural language, we are able to understand and reason without understanding every word. So, for example, that are non-native speakers, usually they understand the sense and they can
maybe I'll also address it. What you're talking about, Ina, is with the NLP models. Basically, we had Thao showed us that they do use an NLP LSTM-based encoding for the language. These models, they work even if a word was not in the lexicon, even if there was the word didn't exist in training, right? But then, of course, the encoding won't be relevant to the new word because the network has never learned this new word. So the accuracy or the prediction or will be lower because this word was never in training. But still, there won't be any exception when you're running, because what's happening is you have a set of characters, you're running it through a neural network, which is basically, you know, transforming the characters into numbers and then calculating over numbers. This will happen, okay? Just the end result might not be what we want it to be. There won't be an exception on the way, if that's what you were asking. True, it's not like a person in this case, because it depends how you train the model, the language model, if it's trained to recognize stuff it's never heard of before or not. But usually in language processing, we don't, when we're doing research, we don't look at this. We put this as a different task for something else. Okay, maybe this is answering the question.
Okay, thank you.
Mm-hmm. Any more questions, anybody? I have two. Thao, first of all, I want to ask, training time. What was the size of the training set? Let's say for the video network. What was the size of the training set, and how long and what type of hardware did you require to train?
I train on a I think a P100 GPU of 32 gigabyte. it took around 12 hours to train the network. It depends on how large the data you train.
Exactly. 10 hours to train the network, the video network?
The video network, 10 or 10 to 15. It depends on the task and the number of data, the data you have.
It's a very low amount. How big was the data?
For the data, I had to do pre-processing beforehand. Let's say I have to extract the ResNet feature first. I have to extract the motion feature first. Yeah. Although I didn't count into the training time. So
Okay. Yeah.
Altogether would cost you pretty much a day.
That's still okay. That's still fairly quick for video data. Just
Yes.
one day. How large was the video data? How many? What was just the raw size of the video?
The raw size of the video, this is a very short GIF. So each GIF less than 200 frames, and there's about 150,000 videos.
150,000.
150,000, yes.
Okay, yeah, that's okay sizes then, yeah. Because for the audience, usually when we do training on video sets, the problem there is training time, because you gotta separate the different the different frames, and then each frame you do image processing on top. Here, because the ResNet encoding was used, it's a bit more comfortable. The training time is a bit more manageable.
Depends on how you extract it. So if you represent a each frame wise as a vector, it would be much more compressed. But if you use a grid feature, which is like 2D feature to represent each frame, then it would be very, very expensive.
Another question is, during your research, what were you trying to do, which you found that is not succeeding? And why did you choose to do it in the beginning, and what were you able to learn from it? That's a bit more generic question.
Wow, yes, it's actually very great. Yeah, I'm about to finish my PhD soon in half a year, more than half a year, actually. Yeah, so my background is in computer vision, so it's hard to say why I chose this kind of research. But like I'm very fascinated about, as I explained before, because like this kind of work is connecting between two worlds, NLP and computer vision. So yeah, I'm very fascinated to do this kind of research, and yeah, keen to know. And I think that reasoning will be the capability that like machine need to have, enable to assist people, because it need to like think by itself instead of like being hungry data all the time. I mean, you feed like numerous massive data into your model, and then probably you have very good performance, but you don't exactly know what it did inside and how it's infer new knowledge from it. Because as human being, we infer a lot of knowledge from what we observe and what we see. And that's what machine doesn't have. And I think this kind of research is still very, very far from that capability, and we still have many, many years ahead to go. Yeah, the ultimate goal, of course, I want to have the reasoning capability of machine. And I think the NLP people, they somewhat get into that kind of things with the GPT-3 model recently, like a hype on media. I think you heard about that. But like for vision, it's the processing is too big, and we're still very far from that.
So a more towards your research, when you were doing the research, Did you try something or you thought of an idea and you tried it out and you saw, oh, it's not working as I was expecting. It's not working as good as I thought. And was there something like this that happened along the research?
Yeah, I think this is like depends on the personal style of a researcher. In my case, personally, I don't like try and error too much. So when I'm doing research, I usually like write down very carefully all the equation, and like it makes sense in theoretical perspective, and then I start implementing. I don't go into like implementing straight away every single idea I have pop up in my mind. I'm not that style. I would document it very careful because before I start implement anything.
Interesting. We're different in this area. Then I like to sometimes try something and see if it's working or not, and then continue.
Yeah, because the way of research that you find something empirically and then you try a theoretical way to explain it. But again, it's very personal.
True. Also, another question, did you have any unexpected challenges or difficulties when you were running the research? It could be on the theoretical side when you were doing the planning, or it could be on the implementation side when you were doing the code and the training and inference.
Yeah, of course. Every PhD student have a lot of difficulty during their study times. I'm not an exact. I have a lot of problem with like implementation system doesn't work. If you have a great idea, this doesn't work, you cannot be state of the art and no use, because like when you like get into I mean, very crowded field like machine learning, artificial intelligence, and people are very harsh on review a paper, then you find it very frustrating when you spend like almost a year working on a particular problem and then you get very bad review, it turns you down. Yeah, it's happened all the time for all PhD students, or all researchers in general. It's not only students. Yeah, but student is maybe they have like harder time than those who become a professional, because they still in like early days of their research career. Yeah, it depends on like personal circumstance. You might not have very great support from the uni, from your professor. You don't have like great computational resources to implement all your ideas and stuff. Yeah, it's all factors can affect your research performance. And I also have that problem too. Here we can afford to have like big computers like Facebook and Google, and sometimes when they release a very huge model, you cannot train on the machine, and that's also a problem.
This is exactly the things that sometimes we don't know when we get an open source as the user, or like the one implementing an open source. We get it, it's ready, we're working, it looks easy. But a lot of times behind the scenes, there was so work being done we are even not aware about. Like having the, like trying to implement something, okay, we didn't reach state of the art, changing it, checking again, training time, how much does it cost to train? So when we're in university, it's a bit easier because if the university has access to funds and things, so we can use that. If no, then we're blocked, and then we need to figure out.
Exactly.
Yeah. I finished my questions. I have a couple of closing words, but again, if anybody has a comment, a question, it's a good time now. Otherwise, I will say the closing words.
Yeah. Sure, go ahead.
So Thao, really, thank you so much for sharing your research. Very elegant research, by the way. That structure with the CRN could be used for many different types of inputs, not only subtitles and questions, whatever comes next. If you have a 3D modeling of a scene and you want to use that also as an input. If you have commentary, something a bit more you can use. So it's I like the structure, it's cool. Thank you for sharing. Thank you for anybody who participated and whoever's gonna watch this on YouTube also. the community is growing. It's always nice. That's part of the pleasure I get in it, and to see that the people are interested and it's growing, and more people are joining. I am always looking for more teachers, more researchers, practitioners who are really touching the current end of the research and the ability to come and give information and give a talk. So please feel free to send them my way if you know of anybody. Again, I will be sending now the links to where you can find the community, mostly on Reddit, also on Discord, where we have instant messaging chat. This talk, of course, will be recorded, uploaded to YouTube, and all the references will be also uploaded in a post to Reddit. If anybody will have more questions after the talk, you can post them on the same post on Reddit, and Thao will look over them and answer. I also sent a link to the newsletter. That's it. That's it. Thank you all. Thank you so much for joining. And I will be closing in a second, so everybody will disconnect when I'm closing.
Yeah, thank you, Peter. Thank you, everybody, for having me.
Thank you. Bye.